Good evening, everyone. Welcome to the 12th edition of this talks. And here we have Karthik Dantu from University at Buffalo. He's an amazing speaker. You'll get to know about that. But before that, about him, Karthik Dantu is an associate professor in computer science and engineering at University at Buffalo, the founding director of the Center for Embodied Autonomy and Robotics, a university-wide research center in robotics, and a co-director of the master's program in robotics. His research interests are primary in perception and representation for robot autonomy. Karthik received his graduate degrees from University of Southern California and a postdoctoral fellow at Harvard from 2010 to 13. His work has been recognized with an NSF Career Award in 2019, award papers at IEEE MRS 2019, ACM EICS 2019, and IEEE IPSN 2012. Beyond robotics, Karthik is a big fan of cricket, American football, good coffee and beer. That's all. Yeah. So Karthik, it's all for you.
Thank you. Hopefully all of you can hear me. Thank you for coming and staying, I guess, later in the evening in India, early in the morning, US time. This is a newish talk. I haven't spoken about any of this work, and all of this work is very new. So feel free to interrupt me whenever. So again, thank you, Sujit, for the invite and the generous introduction. I will try and keep to the amazing speaker tag. There's a very long title, but essentially what I wanted to talk about was representations and how in the modern autonomy landscape, representations are changing how we reason about autonomy, how they are making things easier. Again, representations are interesting thanks to modern AI ML. There's a whole conference called Conference on Learned Representation. So it's beyond, these things go beyond robotics, but I'll talk about 3 pieces of work that have happened in my group in the last 6 months to a year, all of which are under submission. Before I jump in, I thought I'd give everyone a brief introduction about the things that are going on in my lab or have gone on for a while. As Sujit mentioned, work in my lab is related to robot perception. So in the perception stack, we've worked sort of spatial perception specifically. I don't do a lot of high-level semantics, but in the spatial perception stack, going all the way from sensing. So again, I'm a computer science faculty. I tend not to build hardware, but I have collaborated in building hardware. So sensing-wise, we've done a bunch of work. I have a long-term collaborator from University of Florida who builds sensors, and with him, with his group, we have worked on zooming LiDAR, pan-tilt LiDAR, sort of being able to change the field of view of a LiDAR. And there are a couple of papers from before, part thanks to a joint project from the NSF. Another longer term work I have done with a bunch of collaborators at UB is in sensing recyclable plastics. This is thanks to multiple grants, one from the NSF, one from Remade, where we have explored spectroscopy to detect plastics. We have done multimodal plastic sensing. This one was actually published earlier this year in Nature Communication Engineering, and then thermal, using thermal sensing to identify plastics. This was published a couple of weeks ago at Robotics. So this is at the sensor building level. A bulk of the group's work has been in visual SLAM. So we have done a variety of things. So Wi-Fi assisted SLAM, now going back a few years. Being able to run SLAM in real time on edge devices, so edge assisted SLAM, again, going back a while ago, these were supported by my career award. As any of you who have run any SLAM system must have faced, like making it work reliably always seems to be a challenge. So we did a detailed performance characterization, which was a transactions paper in 2023. More recently, in order to speed up these things, we've, in collaboration with with my colleague at Simon Fraser, I've done a bunch of work on GPU-assisted SLAM. How do you take some of the compute-heavy, the optimizations, and make them faster using a GPU? And there's a bunch of papers there. And finally, through a lot of this work, particularly through the performance characterization, we thought we could build more modular and somewhat memory safe SLAM framework. And we spent a couple of years building this bigger SLAM framework called Bauhaus, which is completely built in Rust. And I guess when we started, I didn't know how complex switching to Rust was, but I've learned, we have learned a bunch. And that's a paper that's under submission. So that's in the visual SLAM. Going up a layer, we've done a bunch of work on feature reasoning, including reasoning about feature permanence. So many robots visit the same places. how do you reason about slight map changes in semi-static scenes, like your chair moved, the trash can moved? Can I reason about these things in a SLAM person? And so that was work from before. We've done some temporal reasoning. This is actually work by Karthik, who is in the audience, my PhD student, on like reasoning about consistency across sensors over time. You usually have an IMU and a camera. Can I reason about consistency? And then spatial feature reasoning. This is a work we call Pixar, which was published at CRB earlier this year. And another student of mine is interested in adaptive illumination. This is actually a fun topic that I don't know if is conventional in the traditional autonomy, but I'll show you one of the field things we were doing was in really low light scenario, and we were asking, how do you do illumination for improving SLAM? And so he did some work. So this is part of culvert inspection. And so his first work was adaptive illumination for culvert inspection. This was published in ISA last year. And then he said, can I do this more generally, not just very specific for that application in dynamic illumination scenarios? And there's a whole system that we built based off that. More recently, say in the last 3 to 4 years, the thing that's been most exciting to me are some of the field work we are doing, and that serves as a broad sort of base for motivation, autonomy motivation for my group. So this includes this culvert inspection. This is in collaboration with the New York Canals Corporation. We just signed an MOU with them. So I'll show you a quick video. So I don't know if this is very visible. I wish I could make it full screen. So this is the Erie Canal. It's a 350-mile canal across the New York State. The canal was built 200 years ago. And so there's a lot of wear and tear. The canal itself is this, so I don't know if you can see it, but there's a water body. But if you go further down the bank, under the canal, there are these things called culverts, which are small tunnels, and they occur every mile or so. So there are 350 to 400 tunnels under the canal. And this is for if there is flooding and so on, for water management. And those were also built 200 years ago. So they need to get inspected very often. And so we wanted to see if we can use our legged robots for autonomous inspection. And so this has been an interesting sort of scenario for various research problems, one of which is stable locomotion of legged robots in fairly unstructured terrain. And again, this is on a nice sunny day. We are in Buffalo. There is snow 4 to 5 months of the year when the terrain is completely different, rain and so on. And so if you can see, it pans around, that's the culvert. And this is, again, a bright summer day. Even then, there is a little bit of water in the canal. And so there are a suite of challenging conditions that affect the stability of locomotion and so on. And once you get into the canal, as you can see, it's bright outside, very dark inside. So that adaptive illumination work was motivated by, and here is with our adaptive illumination, it actually looks nice, and you can actually see something inside the culvert. So this has been a rich testbed for various autonomy problems. A second one is there is a local company called Moog. They're actually a multi-billion-dollar motion controller company, but headquartered in Buffalo. They gave me 2 mini excavators and said, can you make these autonomous? And so here is the excavator running in the test area where we work. Again, I had not worked with these larger outdoor vehicles. Sorry, it's very short. But this has also been an interesting learning experience for us with pneumatic control. The mini excavator is 4 tons, 10 feet by 10 feet by 15 feet. So they only get bigger from there. And so working with these bigger machines and thinking about safety, I have a PhD student working on safe planning, specifically how do you enforce safety in something like diffusion. And then we are doing a bunch of work on modeling terrain, detailed modeling of the terrain, and then how do you actually build perception as well as control to do excavation tasks, and that's been interesting. And finally, the third thing is a collaboration with NASA. We call this project VISTA, or Vegetation Informed Sensing through Active Mapping, mouthful. But the idea is to use a whole range of sensor information to understand plant ecology, and we are using hyperspectral, thermal, and we are flying our UAV at the site in Virginia, where there is documented So it's a part of University of Virginia, and it's called the Center for Sustainability there. They have 2,900 acres where they understand land, what the land has been used for the past 150 years, and they plant specific things. And so we have some ground truth on how it's been used. And we are now trying to use these sensors to understand both diurnal patterns. Turns out plant productivity changes morning to afternoon, and seasonal patterns. And we're going to go do some flight experiments in second week of August in Virginia. So that's my very quick summary of things that are happening in my group. I have a fairly large group, and I'm always looking for good students who can do, who are interested in doing fun robotics things. I want to say real robotics things, but as real as an academic can get, right? So I'm sure there are people from the industry who will say, what we do is not quite real, but sort of deployed things such as this kind and find specific challenges in that space. So you see that in this, I have not talked about representation at all. So there's a whole work about representations that I will talk about now. So let me jump into, so the rest of the talk is sort of built on 3 pieces of work that's been done in my lab by 2 people. The first one is work by Pranay, who is seen there. Pranay is a senior PhD student. Let's call him an NTR PhD student who will finish up soon. And this is work in collaboration with ONR, or the Office of Naval Research in the US, specifically with the Marines who think about being deployed in very unstructured terrain. And the work is on planning in large-scale unstructured terrains, and specifically what abstractions do we need to perform that style of planning. So the motivation can be there are many applications that could use this. Think of disaster response after, say, an earthquake, thunderstorm, any sort of natural disaster. You want robots to cover typically tens to hundreds of square kilometers of fairly unstructured terrain, or terrain that you maybe don't have a great view of. We can have some satellite imagery, but the terrain itself is different. And applications can be things like search and rescue, or potentially some sort of, so this is most not as unstructured as was agriculture. But again, our motivation was from this ONR project where we wanted to do courses of action planning. And what that means is you have a team of Marines that get deployed and need to sort of either navigate or cover a given region. So there are multiple agents, human or robot, and you want to give them not one plan, but many options of plans. So they want several courses of action. And so how do you do that style of planning over large regions? And so what you need is, oops, sorry, I did something that, okay, hopefully you folks can still see my screen. So what we want is scalable terrain representations. And the terrain representation is specifically for planning, right? So it needs to understand what matters for planning. So this is the first order sort of description of the challenge. So here we have 3 maps. This one is a 9 kilometer by 9 kilometer area, 50 by 50, and 100 by 100 square kilometer area. And as you can imagine, if I used a regular grid, my planning complexity goes up exponentially. 24 seconds might not seem like much, but if I have to do multi-agent and consistent replanning, the queries go up. And so this sort of compounds fairly quickly. It is also not clear if you get what you want, which is you need to have not just a representation of the space, but some understanding of what is in that space for the planning, because the way humans might traverse this might be different from a small ground vehicle to a large ground vehicle, and so on. So here is a reconstruction of a small piece of land using a few of these abstractions. So you can grid it, you can tile it in a hexagonal manner, or you can tile it in an adaptive manner using a quad tree, where the quad tree focuses on greater detail where there is change, and lesser has lesser amount of representation where there is not a lot of detail. So our framework is called Clear, and that's what is shown here. This is the original space, and you can see the various ones. So some of the issues with doing any other form of abstraction is that they don't capture the things you want. And what you really want is what is the elevation, what is the land cover. Like those affect like how a human would walk on grass versus gravel versus clay. is different. How the human would walk on an incline versus a flat terrain is different. Uh, same goes for like a wheeled or a legged robot. And so you want some amount of semantics, which is typically land cover, and then this geometry. And so this is what our abstraction aims to achieve. So like I mentioned, our abstraction is called CLEAR, which stands for Connected Land Cover Elevation Abstraction Representation. My group is great at making up acronyms. And so the process is simple. You take satellite maps where you have land cover elevation information, and then through a process of decomposition, you come up with a representation that allows you to do planning, quick planning. So what CLEAR does is build sort of a semantic geometric planning layer, right? It has a couple of properties that are useful for various reasons. So it ensures that all the regions are convex. And then it, of course, we wanted to preserve sort of the relevant boundaries, whose transition affect planning. So here is a first order analysis. So this is an abstract area, and all I'm showing here is that some part of that area is different from the rest of it, right? So let's say these are two different types of land cover, and these four things show you different types of gridding you can do. This is a square grid, hexagonal grid, this is the quad tree, and then this is what CLEAR does. So you have some amount of detail around the borders, and when it gets to being uniform, it has lesser amount of detail, and each region is convex. So that sort of visually gives you an idea of what CLEAR can do. So let me quickly jump into how we do this. Or first, sort of some sort of a quantitative measure. So this is telling you, again, how many regions a given area is split into. Again, this is a more complex map than the one before. There is some amount of variation in the land cover as shown by the color. Sorry, maybe the color is elevation. And so there's some amount of variance in elevation as shown by the color. And again, you can see how CLEAR plans the detail across these things and how it combines regions in a certain way. Another interesting thing, which I will describe in a bit, is that CLEAR also, the number of regions is tunable. Of course, how well you capture the underlying terrain depends on how many cells you give, but that number of cells is a parameter that you can pass. So here we are giving something comparable to the other sizes. You can make this much bigger, in which case there will be more detail, but the planning time and so on will take more. Or you can give it less, and then the accuracy of the land cover representation will be lower, but you will plan faster. So this is now jumping into sort of the evaluation of CLEAR across. I guess I didn't quite describe how we do CLEAR. So maybe I can give you a quick sort of idea of how this is done. So the basic idea is we start by placing seeds in the space, and these seeds are placed, think of them as points. They're placed, there is greater number of seeds around places where there is a change in the terrain, in some parameter, the terrain type, the elevation. And then we just do Voronoi decomposition. So that's how you get the convexity of each of the regions. There are multiple other steps. So once you have the first level of decomposition, which we call the boundary seed decomposition, which is you place seeds around the boundary and decompose them, you look at each region and say, is this uniform in some way? Is each region uniform? So the region uniformity means is the terrain, is the elevation varying more than something? If it is, then we just split that up again into 4 subregions. And each of those, you do the same thing. So in a recursive fashion. You also give labels to each region. And the labels are some sort of average elevation, the dominant land cover type, the gradient, if there is one for each terrain. And so there's a bunch of metadata that gets encoded into each of the regions. And as I mentioned, the number of regions, the budget is controlled by a target seed count. So when we place the initial seeds, they adhere to some size requirement of the representation. So why are we doing all this? You can do, so the convexity actually helps with a bunch of planning types. This is something that we need to explore, but there are discrete continuous planners like graphs of convex sets, which is work out of Rastadrek's group, which can do discrete planning, but also do some continuity. And I think a representation like this would greatly assist doing that sort of planning. Like typically we think of planning as just discrete, like A star, or continuous, like uh, chomp stomp or any of these. You can do a combination with these that'll allow you to optimize for the specific requirements of the plan. Okay, so hopefully how we build that is clear. So let's now look at, does this do the things what we want it to do? So this is a quick check on how well Clear captures the underlying region. So here we have taken 12 maps. These are 3 square kilometer maps. They vary by how complex the terrain is. So it's shown by the entropy. Greater the entropy, greater the variance in the terrain type. We have done abstractions with Clear as well as grid, hexagonal, and quad tree. And this is sort of an involved graph. So what this is showing you is mean RMSE on the x-axis and mean IOU. So RMSE measures the variance in each individual region of variance in elevation, right? And so you want this to be lower because we want uniform elevation in each region. The y-axis shows mean IOU, right? So once I have the abstraction, if I reconstruct the terrain, so I now have information about what the elevation is for a given region, what the land cover is. I'm going to assume it's uniformly the same land cover, and the elevation and the incline is the same. And the mean IOU captures how much of the given land cover type agrees with the land cover type from the original map. So what is the intersection of the commonality between what is in the reconstruction to what is in the original map? So you want this to be as high as possible, right? So I want it to be exactly the same type, and then I have fully reconstructed the terrain type. And what we are showing is the various maps for Clear are shown as stars. The grid is square, hexagonal, quad tree is a triangle, and so on. So you want the RMSE to be low, you want the mean IOU to be high, and you can see Clear sort of, the reconstructions from Clear are all in this region, whereas the reconstructions from the others are in different sort of lower IOU or greater RMSE and so on. And so as a first order, being able to reconstruct the terrain I'm representing, Clear actually does pretty well. Now to the real thing of planning, right? So end of the day, we want this to be planned well. Planning requires a few things. So while we are reconstructing the terrain, how a robot does on a given terrain depends on the dynamics model of the robot and how it would vary based on the terrain type, etc. We have work from our colleagues on the same project where they've built. So this is a simulator called BeamNG, which simulates what motion in a realistic fashion, the dynamics in a realistic fashion, even on unstructured terrain. And we have cost models from them for this vehicle, but we have also done this for humans and so on. And these videos are showing you, so we primarily tested, a lot of this tests happened on 3 separate maps. These are maps that are popular in doing this sort of unstructured terrain. So those numbers I gave you in the first slide are not arbitrary. The Wharton map is a 9 square kilometer by 9 square kilometer map. The Humphreys map is a 50 kilometer by 50 kilometer map, and the Mount Rainier is a 100 by 100 kilometer map, so much larger. And these are shown as W, H, and R in this graph. And you can see the videos of these running. We compare these to a bunch of basic planners, A star, RRT. So if you have a fine grid, A star is really as close as you can do in terms of the shortest path, right? So path length-wise, Clear is fairly comparable to A star, like negligible difference. The abstraction time, we have some abstraction time. So the building of the abstraction takes a bunch of time. But once you have the abstraction, the planning itself is pretty fast compared to all the other tricks. And as the complexity of the map grows, you can see that the planning time is really fast. of course, it takes time to build the abstraction on larger maps. And hopefully there's a one-time cost, and then you can do planning, replanning fairly quickly. The other thing is if we enforce constraints like robots can't go over a significant incline and so on, other maps fail because they're not really representing those things. Whereas with Clear, you can get 100% completion. Also, yeah, we don't even take into consideration metrics like how much energy is in a robot and so on for these longer term planning. And I suspect these will fail worse with other such challenges. So hopefully that gives you a sense of how well Clear does with planning. There's a lot more in the paper in terms of evaluation. We take, I think, 10 or 20 start-end pairs across large distances and do the planning repeatedly and show how Clear does. The other thing we did was, so there are newer planners that actually reason with multiple resolutions. There's something called AMR A-star, which is a multi-resolution, multi-agent planner from Max Likachev's group, ICRA 2022, I want to say. And so we compare with AMR A-star, and we do much better, several times better. Similarly, the cost model. So we took a cost model of the robot. So we wanted to see if the abstraction would work if the cost model changes. So we took some work out of Dinesh Muracha's group. It's a paper called Turk. I'm now forgetting when it was published in the last 3-4 years, where they have a learned cost model for the robot, and we plug in their cost model. And again, for any of these measures, Clear does a lot better, several times better in terms of planning efficiency, meaning overall cost, as well as the planning time. So to summarize Clear, so basically, if you wanted to do unstructured terrain planning, this is an interesting way of encoding the information you want to plan in unstructured terrain. The abstraction, though, is still flat, meaning I pick the number of regions I can have, and then you have a flat abstraction. And the challenge with flat abstractions is, again, if you want to scale across many, many queries, and you need many, many queries, especially if you're doing multi-agent planning or and specifically multi-agent replanning. So things change in this unstructured environment. And if I have to replan because it rained in some region or there was a secondary earthquake again in some region, it gets fairly complex. So we were wondering if we could build a more tiered abstraction where I can do global updates for events like rain or some other thing. So there is, in the case of our driver, which is for the Marines, they might not want to go in some region. So they learn something that is tactically, do not go into this region. And so you know how to replan that avoids that area, that sort of thing. How do you do this sort of quick planning, replanning on these large maps? And so for this, we built, so these are the reasons to do this. So again, I didn't talk about heterogeneity. So you can have humans, small robots, large robots. And so you want to plan across agents, and each of them has different cost models, but also different, how they traverse on different terrain types would be different elevations would be different. So reasoning about all this, reasoning about weather changes, and then when you're doing task allocation, doing quick, efficient queries. So we built something called HOPHY. HOPHY stands for hierarchical off-road planning using hypergraphs. And the idea is to take a representation like Clear and then build something abstract where you can do these higher level reasoning, but still do planning on abstraction with finer details, so you get the efficiency. So you build the abstraction, so you have input, again, the same thing, land cover elevation type, and then offline you build this whole abstraction. And what you do online is, so this is all built offline, and then online you do these higher level reasoning at a higher level of abstraction, and then you do the planning at a lower level. Sorry, should I pause? Is there a question?
Yeah. Yes, there is a question in chat box, which is I would like to understand the nature of Autonomy cell decomposition. Can it lead to neighborhood cell influencing coarser representation for terrain demarcation? That is. So
Autonomy cell decomposition. Okay, let me quickly. Can it lead to coarser representation for? terrain demarcation. So maybe what you're saying is that will it create a cell with different terrain types, right? So there is heterogeneity in the terrain type. It can, and in that case, we do. So that's the second step for the thing. I don't know if I did a good job of describing it, but first you do throw the seeds in, and then you do the decomposition. Then you inspect each cell. If there is great variance in the terrain type or the elevation, you further decompose it. You break it down into 4, and we ensure convexity in that second step. So you want to end up with regions that are somewhat flat in the elevation, so within a certain variance in the elevation, and then fairly uniform land cover. So both those things need to happen, and you do a recursive decomposition until that happens. Did that answer your question, Karthik? Okay.
Yes.
All right.
Yes,
Great.
yes.
Okay. Thank you. And again, I should have said this up front. Please interrupt me. Like I said, this is a first time talk that I'm giving. I've not given this talk before. And so if something is not clear, I want to make sure I address the questions. Okay. So on to HOPHY. So this is the hierarchy of HOPHY. So you get the land cover elevation. That's the L0 layer of the map. From this, you can get fine regions, and this can be clear. Since I've explained clear, the easiest way to think about it is this is basically clear, but you can do this in a variety of other ways. From this, we build what are called GS nodes. These are geometric semantic nodes. And the GS nodes are a combination of similarity between the nodes in region, either in terms of elevation or in terms of semantics. So you can have, for example, all these. So there's a bunch of regions here which have similar land cover and potentially similar elevation. And so all of that got abstracted into one big geometric semantic node, which did not happen at the base level because there is a certain number of seeds that were assigned. And so there was much finer detail, right? So you're basically combining things that are similar in terms of elevation and geometry. And then finally, you
Professor
build
Karthik, I have a quick question.
Yeah.
So when you say like it's similar to, like, why is it? I mean, I'm trying to understand, like, why do you call it geometric semantic? Like, what is geometric
each of
similarity?
those nodes have similar geometry and semantics. So geometry, elevation, semantics, land covers.
Oh, geometry, when you're saying geometry is like in terms of
Elevation.
topography of the region. Elevation.
Yeah.
Okay.
Yeah.
Okay, cool.
Yeah, I didn't mean the geometry of the
cell.
region,
I
the
thought
shape
it was
of
geometry of the
There's
shape.
nothing to do with the shape of the cell.
Okay, cool.
It's just the geometry of the region of the topography. Yeah.
Thank you.
And then we do another level of reasoning where we now build hyper edges. And again, we are showing you something, but that visual is not exact because these don't need to be contiguous. So these are hyper edges between these graph nodes. And what they encode is things of similar land cover, basically, but things that get affected similarly, right? So that's what this roughly does. And again, I want to stress this. This is just a visual. I don't think this is exactly how it is because they're not continuous. These are hyper edges in sort of hyperspace, and we can't quite show that well. So when we do this on a map like Wharton, for example, we have something like 65,000 fine regions here. This becomes something in the order of 12,000 semantic nodes, or 100% to 20%. And then this becomes something like 134 regions. So 1% of this. So there's a large reduction in the abstraction as we go from fine regions to what we call coarse regions. Again, not very creative naming, but so that all of this happens offline, and these hyper edges are not of a single type. So you can have hyper edges that connect GS nodes that have similar land cover, and that's one class. You can have similar grade, meaning similar slope. You can have things that get affected by sort of how weather affects these things. So you can build a bunch of these hyper edges that are that allow you to reason faster online, right? So here are some examples. And again, it can be agent specific, weather specific, just terrain specific. And you build a set of these, and you don't need to use all of them at the same time, but they're just logical connectors that group a set of GS nodes that have similar properties of some type. And now when something happens, I can update this at O of the size of each of these hyper edge instead of trying to scan everything. And this is because, again, the more detail in the paper, but you can do set operations on these hyper edges and affect the all the GS nodes in that region in one quick update. So there's another question.
Yes, I just wanted to ask, like these GS nodes can have multiple of these hyper connections, right? Like
Yes. So they can get affected in multiple ways, but typically you affect one thing, right? So let's say there was rain in some area, you apply that to sort of one set of hyper edges, and even there it's sort of geometrically aligned. So it rained in this small part of the whole map, and so I take the hyper edges and then I sort of constrain them to GS nodes to sort of that area, and then I apply the weather event there.
Thank you, sir.
Yeah, so the cell sort of filtering affected sets instead of doing it on the whole graph. So this is now, we did this many times, right? So if there is weather, so how does this higher level of abstraction work when you're doing queries when you want to do repeated queries, and the queries vary by distance. So when I'm trying to do a path query, the start and end point can be short distance, long distance, and obviously that affects the number of regions that need to be queried, and correspondingly the computational time. So this is a log scale on the y-axis in terms of time in milliseconds and the distance. And the blue shows you A star query time. The red shows you find region query time. So if I just use clear and did queries on clear, and of course the green shows you HOPHY. And again, you can see the order of magnitude difference in the path length query time. Now, you might ask me, of course, you have very few regions, the query time is lower. It also affects path quality. But again, I've not spent the time to describe the algorithm, but we do a coarse to fine path query. So coarse where in the hypergraph space, and then we query in the fine. So the path lengths that you get when you do queries on HOPHY are statistically comparable to A star. So your length accuracy, there is in the 3 to 10% difference, but they're really not a lot of difference. So you get fairly accurate paths, but the query time is 2 orders of magnitude faster, 3 orders of magnitude faster than A star. And of course, I mentioned this is most effective when the queries are, when you have many queries, right? So this is now, we do an update and then we query after an update. And the question is how much time does it take? Again, this is a log plot. The y-axis is the path length. The x-axis is the query time after the update. And you can see we are in the millisecond range. So HOPHY is millisecond to tens of milliseconds. And based on the path length, A star can go in the order of hundreds of seconds to ones to hundreds of seconds. And clear goes from tens of milliseconds to ones of seconds. So the hyper edge update, and this is where we win, which is it's going to be super fast. So the update time is really fast, and the cost changes match A star very accurately because of the way we build hyper edges. And this is now an example where we do mission planning for multiple agents in a fairly reasonably complex environment, 5 agents, 50 tasks. And for this, we use like the MTSP, min-max MTSP, which is, again, NP hard problem, but we use a heuristic that works. And so doing this on our abstraction gives you in the order of like 2 orders of magnitude speed up over A star, while providing very compatible matches. Okay, so I've already gone over half the time. So I've presented a couple of abstractions to do unstructured sort of planning on terrains. There is clear, which says how do you take large outdoor terrain and then build a representation that can do planning, and HOPHY, how when I want to do repeated missions or I want to quickly update query many times, how can I build a tiered abstraction that gives me accuracy, but also gives me the efficiency in the query time, planning time. So like I said, the lead student on both of these is Pranay, and we have so my group is Drones Lab, droneslab.github.io, and most of the projects are droneslab.github.io/this. So that is clear. There's also HOPHY, and you can scan the QR code and get things. So this is another abstraction work called GOLF, and GOLF stands for Graphs over Lagrangian Fields. And this is work led by my postdoc Charu, who is shown there. And this is work supported by Moog and work with the New York analysis. So I spoke about unstructured terrain outdoor. What if you want to do this more generally, right? So indoor spaces are tight. You want to do navigation around people and so on. And what I would like is an abstraction that allows me to plan. Like the abstraction should adjust to the space. Some spaces are more complex, some spaces are less complex. And I would like the abstraction to adjust to that. And things like quad trees sort of do this, but they don't give you the power that I want, which I will describe fairly quickly. So here is an example. So there's a grid layout, and this is some abstraction that sort of puts points around where there is detail and lesser where there is no detail. And this is what I would like, right? So this is what golf is. And again, it's a graph. That's what it says, like graphs, and over Lagrangian field. So if you reason about space, there are a couple of ways of reasoning about space. There's the Eulerian way, which is sort of reasoning in some global coordinate system, and Lagrangian space, where I'm reasoning locally. So I model everything as things that are local, and that's what golf does. So it connects locally. And I don't know if you can see here, this is sort of an abstract map where the edges are curved, which is more complex. So all the gold points are, and you can see a lot more detail on the boundaries and fewer where there is not as much space, right? So the way golf does is you get the map in some way, right? So let's say you have a template like this. You initialize by throwing in a grid and having points uniformly. Then there is a process of refinement, which has 3 rules, and I will talk about them in a minute, that moves these points to adjust to the space, right? And then finally, after refinement, you get this graph, and then I do the planning in that space. Okay. I don't have the detail. Maybe I will leave that. So how complex is this? So we took the floor map of the Metropolitan Museum of Art. This is, forget how big, but fairly large. So if you had a map that had a square grid that had grid cells at 10 centimeters, it would result in 7 million points. And golf does this with 68,000 nodes and 264,000 edges, builds it in 60 seconds, right? So this is a drop-in replacement for any representation you have. So typically, if you see an autonomy pipeline, I build a map, I throw it into an occupancy grid, octree or something, and then that goes into the planner. You can take that octree, remove that, put golf in, and you can do the planning. We have done this with various planners, so A-star, of course, but there are newer planners that can reason discrete planners, so theta star, beta star, and we do orders of magnitude faster with this. So the advantage of golf is not just that it is this sort of an adaptive occupancy. The awesome part about this is I can represent other things beyond occupancy. So for example, we took the application of social navigation. Social navigation is, I want the robot to move around a dense area where there are people moving around. And I have constraints like I want to take the shortest path to where I want to go, but I also want to be conscious of people, right? So social navigation, again, is a well-studied problem. There are metrics for how you define a good plan. I don't want to be in a person's personal space. So I don't want to get this close to the person so that the person is uncomfortable, in terms of how close we are. We do this when we walk around. I don't get into the face of another person, even though that's not exactly a collision, right? Because I don't want to be in that personal space. So there are a bunch of these metrics, and you want to plan across these metrics. So we took golf and we sort of adapted a previously proposed RL algorithm. It was called SARL, I forget what the full, and we call ours Sage RL, sort of golf enabled SARL. And sorry, I should just jump to the result. So the planning runs like orders of magnitude faster. All of this is, again, mainly because of how we represent, how sparsely we represent things that don't need to be represented, right? So particularly with a uniform grid, we do a lot better in terms of planning time. But even with adaptive things like quad trees and so on, we do a lot better. Paths are very comparable, especially in realistic plans. So that curvy one is where we are worse. But in regular floor plans, and we have done, I think, 20 of the floor plans and 10 start goal pairs for each one. And so we do really fast. Again, in terms of the social navigation, we are very good. As the map grows, what we have found is many of the state-of-the-art social navigation algorithms don't scale because they're all RL-based and they don't have the ability to see things forward. Whereas we can, when we build the representation, the underlying golf representation, I can represent a person as a subgraph, and I can encode things like their velocity. And now I can project forward where the person would be 5 seconds from now when I'm near them. And I can adjust my speed. So this is sort of a rough architecture of this. So there's the occupancy map, and we build like this GNN that builds the underlying graph. And sorry, the refinement happens using this energy-based strategy that's three-pronged, and that evolved the graph. We then train these GNNs, and the GNN can be just the shortest path. I can query occupancy using a GNN. I can query where the person moved using the GNN. So I can encode a bunch of stuff that I want to that have to do with the local physics, right? So the velocity of a certain set of vertices, or the speed, or the acceleration, or the force, and so on. And you can use that now for the planner and do a lot better planning. So golf is very general, and you can do a bunch of other reasoning things. We are just scratching the surface on this. So here is an example of it being used in a completely different place. So this is now a pick and place task. What is happening is there is a robot that's picking up that block, and it's picking up the red block and putting it on the green block. What we are showing you in the different colors are the various interactions. So the orange graph is showing you where the gripper is, and the interaction with the block. And when it's being placed, you can see another yellow graph that describes the interaction between the red and the green block. So using golf, you can reason with a bunch of stuff. So my understanding, I'm not a manipulation person, but talking to manipulation people is like they want to reason about how you place it. There might be a delicate object that I'm placing, and I don't want to use greater than some force, or I want to reason about if I placed it on an uneven surface, what the physics would be in the future and how I should place it for stability. You can do all of that using golf. And you can do a bunch of other funky stuff. So this is now a mesh with some temporal model. So it's changing temporally. Think of like your cloth, right? I bend the cloth and it changes, it deforms in a certain way, and you can represent that as a mesh with a PDE, which describes the physics of how it will change over time. And this is, on the right side, is how that is shown in a uniformly defined mesh, whereas on the left side is what you can do with golf, and the representations are much richer. So I can do things like modeling turbulence, modeling soft body physics, any of these things, and so on. And so golf is like super general. Again, this is another application that we built. So this is now thermal diffusion in a plastic. This is work that we've done in a previous paper where we model thermal diffusion, but this is now represented using golf. And golf here is not just a spatial representation, but a spatio-temporal representation. So on the y-axis is time, and what is shown here is the raw thermal field. So here is a material, I'm heating the material, and how the heating and the cooling happens over time. This is a raw field. If I did uniform sampling, that's what this would look like. For each of the temporal slices, if I represented used golf, this is what it would look like. And here is a joint space-time representation using golf. And you can see how sparse I can represent this. And for the downstream learning, the sparse representation would be greatly helpful in doing any sort of downstream learning. And we're just experimenting with this now. Okay, sorry, I wish I could have spent more time on golf. I'm really excited about this work, and there is a lot of power to sort of encoding locally these sort of physics attributes and building that into a representation. And now just doing small GNNs to learn how these move forward, again, with the discussion of things like world models and so on. Now, building succinct representations allow you to train, learn, forward models, predict in the future, and so on. And I think golf could be a really nice abstraction to do a lot of that. Again, this is work led by my postdoc, Charu. And you can, again, go to droneslab.github.io/golf to understand that. Yeah, that was my quick golf pitch. I'm happy to stop and take more questions.
Thanks, Karthik. Yeah, so the floor is open for questions.
So in the golf part, from like starting from the, like you start with a grid world, right? You lay over a grid and then you start refinement, right? So like on what basis these refinement occurs? Like
Yeah,
what
so
is
there is an energy formulation.
okay?
You have the base map, right? Let's say the floor layout. We use that as input. You can actually also use things like standard images and point clouds and so on. So the input to golf can be any number of things, like a regular slam type thing or splat. We can take a bunch of stuff. It basically uses that to build. So the energy function gets attracted where there is some gradient.
Okay.
So from the top view occupancy, there's a gradient, sharp gradient around the walls. So there's attraction there. And there are, but if you just had attraction, then everything would collapse into one. And so you have two other functions. One that sort of maintains a minimum distance around the gradients. So there's a specification of minimum. And then there is another constraint that gives you points in a minimum distance where it's flat, right? So where there is no gradient, you still want some points, especially for occupancy and planning. And so there is a maximum distance you can go without a vertex. And so all these three combine into one energy function, and that's what is used for the refinement.
Okay. And since you said key, you can use golf for various other applications, like you said, key use golf for modeling these spatiotemporal processes. So how will we, let's say, if we want to use golf for planning in dynamic worlds where there are obstacles moving, and then the agent itself doesn't know where the obstacle will be moving, but then with adding padding to the obstacle, let's say we want to do safe navigation in dynamic world, will that be possible using golf?
Absolutely. So golf is a representation.
Yes.
Right. So it is not seeing anything you do not see. I need a way to perceive the dynamics. So in the people case, you can do semantic segmentation, and you can assign this subgraph in the golf graph is moving together in a certain way. Once you encode that, I can reason about how this subgraph is moving over time, and I can project forward in time the whole representation. Like I can just sort of roll forward for a certain time and then use that for the planning. And that's what we do in the Sage RL work. So of course, you can also train a learning algorithm. So in our case, we train an RL algorithm to understand once there is the dynamics represented in the environment, in the representation, the RL algorithm uses that to understand, there's a human coming this way, so I need to pause and go after the person moves. And we constantly update the representation. So in case the human is going, but suddenly decides to turn and go the other way, golf gets updated.
So it's also adaptive in nature in that sense.
Yeah. So, and the updates are like super quick. Yeah.
Okay.
Building the representation takes a little bit of time, but the adaptation, like subgraph things, are very, very quick.
And also, what about the quality of the paths generated, like with respect to, let's say, some finer these?
I showed you, I think in the order, like we are single % different.
Okay.
Yeah. So In the curvy paths, we are 5%. In the regular 4 plans, we are about 1% compared to A star at a very fine level. So like super accurate. Like again, because there is so much detail where you need the detail, it sort of plans quite efficiently.
Thank you, sir. Thank you. That was helpful.
So, any other questions?
So there is one in the chat box. Karthik, do you want to ask or should I? Okay, I'll just read the question. So the question is, does this also need some? Okay, it was about golf only, I guess. The question is, does this also need some layer of semantic abstraction of the floor plan as well?
The abstraction itself is the same. I do need semantics to be seen in some other way, right? So if I have to represent a person and the person's velocity, I have to designate some subgraph in the golf representation as the person. How do I know that's a person? I need something to tell me. So some image semantic segmentation that goes as input to golf, and then golf will label that as a person now. And so all the reasoning is on the graph. So there is no layer in the abstraction itself. But you can label subgraphs as some entity. And from that point on, at that instant in time, I can do things like forward move the person 5 seconds ahead and say where it is, or I continuously observe and adapt and build a representation, right? So yeah, the representation, there is no more layers, but to assign any of these local properties, I need some way to observe them. That is my point. I hope what I'm saying is clear. Yeah, I need some external way of telling me this part of the subgraph is unique, right? So this part of the subgraph is the gripper, this part of the subgraph is the object, and this part of the subgraph is another object. At that point, I can reason with their interaction, about their interaction on the graph. Yeah.
So, Karthik, I have one question with respect to the one where you had a terrain maps. So you have I made a say, the graph and I got it, but let's say after a while the terrain beneath changes. Do I need to regraph it or the entire process, or only dynamically change some parts of it?
So HOPHY, the hierarchical version, allows you to do a little bit of change. So at this point, I don't know if we have done any, like if there's a landslide or something. Yeah. So we haven't done a redoing of the thing. But my suspicion is you can use the same ideas from how we built the base abstraction, like clear, doing the second stage, so the seed decomposition, and then the second stage was checking if any part of a region is not uniform and then subdividing it further. I would just run that on the area that is affected, and you can redo. We haven't done that, that's something to show. But I suspect you can just do that. You don't need to do anything else. The global map can stay the same, just locally you can update. But we haven't demonstrated that specific thing. We only worked on weather issues, assuming the abstraction itself stays the same, the costs change. But this requires the abstraction to adapt, and you can do that locally.
Okay, thanks, Karthik.
Other questions? Now or never. Okay.
Okay.
Thank you
Seems
for
like
having
nobody
me.
wants. Thanks a lot, Karthik, for even giving us a very quick, allowing you to quickly talk rather than making us wait for a very long time.
No, like I said, I always have more slides than I can. That seems to be my presentation style. But like I said, my lab is consistently recruiting good students. And so if you are interested in working on any of these and doing some field work, email me. We also have a strong master's program in robotics, which, again, everybody wants roboticists these days. And so if you're interested in our master's program, I tend to recruit a lot from my master's program. And so happy to talk to you about any of that. Just email me. I'm quite informal and happy to respond if you email me. And thank you for
Thanks,
having me.
Karthik.
All
Thank
right.
you.
See you, folks.
Thank you very much. See you. Bye.
Thanks, Karthik.